Okay, in this video we're going to go through some basics in using Simulink. We'll go into something a little more detailed than you need for the first homework, but I'll just cover it all at once that way, and then you've got it. So we'll kind of go through the process of putting a model together and show you the mechanics of connecting blocks and getting blocks and things like that. So step one, if you want to use Simulink, is to open up the Simulink library browser. That's this icon up here. Always reminds me of a little toy train or something. I've got a blown up version over here on my journal, so it's obviously not a toy train, but that's what the icon looks like. There is the Simulink library browser. If I click over here on the new file, it creates a new model. I will point out, clicking here gives me a new Simulink model. If I was back in Matlab, if I click on the new file, I get a new Matlab script, a .m script, instead of a model.mdl file. So depending on where you click, that's what you get. So what have we got here? I've got a blank model over here on the right. I've got the Simulink library browser, and what the library has is just a lot of blocks and things we can use. Commonly used blocks is just a bunch of blocks that you commonly use. Continuous blocks include a lot of essentially the blocks you would use for doing dynamic models, integration, differentiation. There's a PID controller, state space if you've taken your differential equations and put them in matrix form, transfer function if you've taken the differential equations and put them in Laplace form, discontinuities, odd things. So we'll go through these and use these as we go. But what we're going to do is build a model of a DC motor here. So let's take a look at our DC motor. This is kind of a schematic representation of the motor. This side is the electrical part, and over here we have the mechanical part. Starting with the electrical, we have a voltage source. We have a resistor here, which represents the resistance of the wires in the motor coils. We have an inductor L, which represents the inductance of those coils. And we have a term here, back EMF. That comes from the fact that the motor has coils of wires on the rotating part and permanent magnets on the outside. And as you rotate those wires through the magnetic field, as Faraday discovered, you generate a voltage. So, and as it turns out, the voltage that we generate as the windings are rotating actually opposes the voltage source. So if your voltage going from positive to negative is going this way, the back EMF is going that way. Now we can apply Kirchhoff's law, and we can say that essentially the sum of the voltage drops around this loop are equal to 0, or I have the equation here, the voltage drop across the resistor plus the voltage drop across the inductor plus that back voltage is going to be equal to the voltage source. That's a good place to start, and I will start there in a minute. I should probably explain the rest of the model. On the mechanical side, obviously we have a torque generated by the magnetic fields and things. We have some torque, external torque, some load applied to the motor that we subtract, and we end up with some net torque left over. That additional net torque is what will accelerate the motor, and using Newton's law we can say the acceleration is the net torque divided by the rotational inertia. and I'm ignoring the small g to get units to work out, but that's okay. If I've got the acceleration, I can integrate acceleration to get speed. If I got speed, I can integrate that and get the angle or displacement of the motor. So those are the equations on the mechanical side that we need to know. And then we have equations that link the mechanical to the electrical part. What is this torque, motor torque? Well, the motor torque is some constant times the current I through this electrical loop. Okay? And this back EMF is determined, VB is some constant, again, times the speed of rotation. So the faster the rotation, it's supposed to be an arrow. The faster the rotation, the higher the back EMF. Okay, so those are the equations. Let's start with this basic voltage loop, and we can kind of rearrange it a bit. If I know from Ohm's law that the voltage drop across this resistor, my VR is pretty straightforward. It's the current times resistance. The voltage drop across this inductor is a little more complicated because as an inductor we know the voltage drop is the inductance L times the derivative of current with respect to time. So what I'm going to do, because I know ahead of time that when I build these models, I usually start with the highest derivative. You know, in this case, it's just a first derivative. If I was doing other things, I might want to start with acceleration. If I started on the mechanical side, because then I could take the acceleration, integrate it to get speed, integrate it, and it generally works best if you start with the derivative and do integration in these models. So I'm going to take this equation, solve it for the voltage across the inductor. So VL equals the voltage source minus the voltage drop across the resistor. I'll use a capital R. And minus this back EMF or back voltage. Okay, that's pretty straightforward. So what if I were to draw this graphically? I could say that I have VS, VR, and VB, and I can put them into a block where this has a plus sign, this has a minus sign, this has a minus sign, and my output here is going to be VL. Okay. Now I also know that VL from this equation is equal to L times di by dt. I can rearrange that. So di by dt equals VL, the voltage across the inductor divided by the inductance, right? So if I take the voltage here and I divide it by 1 over L somehow, what I get out of there is di by dt, and then I can take that current, I can integrate it, and I get I. Okay? And essentially that's the process I'm going to use to get this model. And okay, let me one more thing while I'm still on sketching here. Once I have I can take it and I can multiply it times the resistance, right? I times R equals VR. So that's times the resistance. The output there is VR, and that is what I needed here, right? VS is a given from the source, and at some point I need to come up with an expression for VB. But as I find all these things one bit at a time, I can put this whole model together. So let's actually do that live. So I'll go back to my Simulink library browser, and I'll need my blank model. One thing I want to do is, if I have a very complex model, I have a motor, I have a control system, I have an external load, this model is going to get very cluttered very fast. So it's nice to encapsulate things or create layers where you put things into sub-layers, subsystems, so you can have one, declutter your diagram, make it easier to follow, make things more portable. So I'm going to click on the Ports and Subsystems tab over here in the Simulink library browser, and I'm going to grab a block down here called Subsystem and drag it into my model. Okay, and I'm going to relabel this subsystem DC underscore motor. Why an underscore? One of the things I probably failed to mention in the first video is Matlab is a little bit weird about variable names and file names and things like that. File names and variables never start with a digit. They don't have spaces in them. If you try to put a space in a file name, there are workarounds, but basically Matlab has a fit when you try to use it. Same thing with variable names. You can't use special characters like plus, minus, times, divide, things like that as the variable name. Matlab has been around for a long time, and a lot of these conventions go all the way back to DOS, and they're just still there. So, okay, so I've got a motor. Something's gonna happen in here. What is my input to a motor? I'm gonna have some input here. So for my input, I will just put a step, unit step, some kind of source. So I'm clicking on sources. Here's a step. I'm going to drag that, click and drag, and I'm going to relabel this source. And if I double click on this block, step time is 1, so at 1 second it's going to do a step, and at 1 second it'll start at 0, and at 1 second it's going to step to 12. So my output will be 12 at 1 second. I'll connect that here. So all I did, well, let me explain that. I click on this little out port on the block, and you can see how my cursor changes from an arrow to a cross. Left click and drag. And as I get over here, it turns into a double cross. I don't know if you can see that very well. And I let go, and it's now connected. I will double click on the line itself, and I get over here a flashing cursor, voltage in. Now I can label that signal. It's always a good idea to label every signal, even if there's some redundancy in the labels, because believe me, when you come back 6 months from now, you look at that and say, what was that for? You just won't remember. And labeling everything just makes it so much easier to follow, so much easier to debug. So I got to, and what am I going to want to see out of this motor? Obviously, the motor generates a speed and it generates a position as the kind of out. So I'm going to go to Syncs, and I'm going to pull up 2 scopes, just so we'll be able to visualize these. And one of these will be speed, and the other one will be angle. Okay, and now I can't really connect the output. I've only got one output. I've got 2 things here, so we'll fix that. So if I go and I double click on the top of the subsystem block, it opens it up for me, and there's not much inside, right? Just an in port and an out port and a line connecting them. I don't need that. I'll delete that for now. Now I need 2 outputs, right? First one we will call speed, motor speed, and the second one we'll get, if we go back to syncs, sorry, I can see the out port here. I could go drag that into the model, or being lazy, if I'm in the model, if I right click and drag, Matlab makes a copy for me. Okay, and I can relabel that to be angle. The input I said was voltage, so I'll relabel that voltage in. Okay, oops. So now, and I'm going to make this bigger and I'm going to essentially drag a box over those two, move them over because I know I'm going to need more room. Okay, so we had this equation here where we took the source voltage, subtracted the voltage drop across the resistor, subtracted the voltage drop from the back EMF, which at this point we don't know where it comes from. So we had a plus, minus, minus, and our output was the voltage across the inductor. How do I do that? I want that window, and I want my library browser. So addition, that's math, right? Math operations. So I can grab either an add or a subtract block. They're really the same thing, and I'll show you in a minute why. I'll just grab the add, drag it over here, and if I double click on the block, it opens up and it tells me a number of things. There's actually some information up here at the top that tells me, how to set this up. Basically, it's plus plus is a list of signs. Well, if we went back to our journal here, we see we want a plus, a minus, and a minus. Go back here, so I can type plus, minus, minus. Okay, and back to this, and now you can see on this block it says plus, minus, minus, and I just grabbed one of the corners and made it a little bigger. So my plus input was the voltage input, the Vs, and one little trick here, if I double click right on that thing, okay, I get my cursor back so I can label that signal. Rather than typing in a name, if I type a pair of angle brackets like that and hit enter, oops, I don't need enter, just click somewhere else. It will go look upstream and pick up the name that I had labeled, the name of the signal I'd used at the higher level. The nice thing about doing this is I see it says voltage in for the signal name. I see it says voltage in for the port. That's one indication that I haven't made a mistake wiring this thing up, because it does happen, and I have done it. And I've caught it this way. It's just really worth doing. So we could change the name of this add block to Kirchhoff's law. I'm not going to try to spell Kirchhoff. The output here, if I just drag it and pull it over, I can label it, even though it's not connected to anything. That's my VL, the voltage across the inductor. So the next step, we took VL, we divided by 1 over L. Couple ways we could do that. We could take our VL and I could put it in a division block, where divide block, you'll see it has a star and a divide sign, and then here I would connect this back to a constant block, and this would have the value of L in it, and then the output here would just simply be VL over L. Or I can use the gain block, which is just kind of an inline multiplication, and that's what I'm going to do because that's simpler in this case. Simulink library browser, pop up my subsystem here. So I'll go to math operations, where I'm already at. I'll grab the gain block, click, move it over here, and if I move it to the point where that little in port touches that end of my unconnected block, boom, it's connected. Double click the block, and what is my gain? Well, my gain is 1 divided by, divided by, and I'll make an uppercase L for the inductance. I could type a number in here. In fact, I will. 0.01 for my inductance, okay? Or I could have typed a symbolic name in there and then used a variable from my workspace, Matlab workspace, which we haven't created yet. It gives me a K. If I make this block a little bit bigger, now I actually see what's inside there. I can label this inductance. The next thing we do in our model was, going back here, we integrate that. The output of this is di by dt. We're going to integrate that, and we're going to get current. So, spent a lot of time going back and forth between windows, but so I want an integrator. An integrator is a continuous block, and there it is. You can see the label integrator, and you see that the symbol on the block is 1 over s. Why is it 1 over s? Well, in the Laplace domain, integration is done by dividing by s. We will get to that in class in a week or two, but for now I just have to deal with the fact that that's one of Matlab's quirks. Okay, one simple way to connect that is if I click there and I do a shift click on this one. Nope, sorry, my mistake. Click there and control click over here. It should have connected those. Oh well, it didn't. We'll worry about that later. So anyhow, this was this signal label DI for D lowercase d uppercase I for the derivative of current. We integrate this and our output is the current. I need now that current I, which is coming out here, and it's going to go several places. I'm going to feed that back into my equation here, right? So I need to multiply that by the resistance. Again, being lazy, I will right click, drag this, oops. Why are we doing this to me? I will right click and drag this block, and I'll right click on it again just to right click and let up. If I go to format, I can flip the block, ta-da, and it'll make it easier to hook up. So double click on the block, I will put my resistance in here of 5 ohms, and I can I've already got the stub coming out of here, but what another way to connect things is to right click and drag, and I can stop and route this any way I want if I let go and it sticks like that, okay? And I can move segments up and down and clean it up a bit. But this will be the resistance, and the resistance times that current is the voltage across the resistor. And well, let me show you another way to connect lines. I can also, instead of going forward, I can go backwards. I can start here where I'm going, left click, drag, I'll let it up for a second, left click, drag, and I'm connected that way. Double click on the line, and this is VR. Okay, so now I've got three things I need to calculate this voltage across the inductor and label this the current I. So that's a good start, right? And we'll just keep going. Now, going back to my equations here, I have the current, and given that I have the current, I can now calculate the motor torque, right? From the motor torque, just by multiplying by that, by the motor torque, I can, if there's a load torque, I can add that. From the load torque, I'll calculate the acceleration. From the acceleration, I'll integrate it to get the speed, one of my inputs, and from the speed, I'll integrate that to get the angle. I'm going to pause the recording and do a few steps just because this is taking a long time, and your time is valuable and I don't want to waste it. Okay, we're back. I have now essentially completed the subsystem. We have the constant multiplication here to get from current to torque. Here I've introduced a load disturbance. If I double click on that, I see that a step time of 15, I will add a 200 unit load to the system. I'm going to subtract that here from the torque generated by the motor. That leaves me with a net torque divided by the inertia from my equations back here. Back up. Net torque divided by inertia gives me acceleration. Again, right there, I can integrate that to get speed, integrate that to get the angle. So there's acceleration, the integration, I got speed, integrate again, I got angle. The speed goes out to my out port to the higher level, the angle goes out, so I got two outputs from this subsystem. Speed gets fed back here to the KB, the back EMF constant, to give me the VB that I needed, and that gets subtracted there. So now I have a whole model with all of the terms built from these basic equations right here, from first principles, okay? And let me go back to this. I hit escape. That closes that subsystem and moves me up a level. I could have both of these open at once and just essentially go back and forth like this. But escape, if I hit the escape, it kind of makes this subsystem go away and I have fewer windows and it's less cluttered. I changed the stop time, that's this number up here, to be 30 seconds. And let's click on Run, which is the Start Simulation button, and we'll see what happens. Dink, it just ran. If you were watching down here in the bottom, I'll run it again. It goes from 0 to 100% faster than you can see. So if I double click on that block, I see I have the speed, and it starts out at 0, 1 second, starts to accelerate up to about 800 units. This load kicks in and it decelerates a bit and stabilizes there. The angle just continues forever and ever and ever. I will admit I ran this before and debugged it. Couple little tips here. This button here, let's just do it, demonstrate live. Okay, if I close those, run it, when I double click speed, it remembered that. Okay, never mind. You may just see when it first comes up, you may just see that much or something. You won't see the whole thing. This little button fits these axes to what you want. Another tip, if I click on this parameters, the second icon, click on history, uncheck this limit data points to the last 5,000. This model doesn't make a difference, but if you want to see a plot of all the data and the simulation took more than 5,000 steps, you have to uncheck that so you don't lose any data. So that is our DC motor. Click on Save. Save often is a good idea, just a general thing. You can see at this top level, again, I used those angle brackets to label these signals, so it propagated the signal name from inside that subsystem, and it shows up here on the scope block as well. So now I see that it says speed here, I see it says speed here, I see it says speed there. It says speed on this output. I have some confidence that I did this right. So that's a pretty complete model. There's one other model I've already built, and I want to show it to you. Let's close this out. Just because there's one of the little quirks that causes problems sometimes, and I'll leave that. This is a model of an RC circuit. View, fit system to view, just to blow it up. So I have a voltage coming into this circuit. It has an amplitude of 1. It has a frequency of 75 radians per second. This is not hertz, this is radians per second. In our equation for an RC circuit, basically dV across capacitor by dt equals 1 over RC times our voltage source, whatever the voltage source is. That's an equals, not a here. Okay, so that's the heart of the equation for that. And of course, we take the dV C by dt, we integrate that, and we get V sub C. What's a C, really? I did the same thing. Okay, never mind. So there's the model. So this is 1 over RC. There's the integrator. I get the voltage. This model only runs for 2 seconds. That's all I need. So I'll run this, and we should see on the scope, this is a mux block right here, this bar with 2 things going in. So essentially it combines the voltage input with this voltage across the capacitor output, and we can compare the two. So I should see a sine wave for my voltage input and a somewhat attenuated sine wave for VC, right? Let's open this block, and ooh, ick, bah. This does not look like a sine wave to me. What went wrong? I mean, what could go wrong, right? I mean, it's just basically this sine wave voltage here as an input should be, it's that yellow line as a top input. It doesn't look like a sine wave, does it? What happened? Well, let's go back to, I bet you I got a warning here. Yeah, I got warnings here. Okay. Warning, this is in my Matlab command window. Using a default step of 0.04 for the maximum step size. Okay, we had a frequency of 75 radians per second. To get that into hertz, it's 2 pi radians per cycle, so 75 times 2 times pi. Do I have to divide? Is that 471 hertz? Do I have to? Yeah. Okay, so we're basically, our input frequency is 471 hertz, 1 over answer. So that means I've got a period of 0.002 seconds per cycle. Well, if this thing was running at 0.04 seconds per update, I mean, I wouldn't even get a complete cycle. So obviously it's running faster than that. So we need to put in a much faster time for our maximum time to make sure we get enough samples. So let me go to our model. If I click on Simulation, Configuration Parameters, there's a parameter here, Maximum Step Size, and the solver is a variable step. You can pick between variable step, fixed step. There's a number of different solver options. Normally the default works, but I'm going to make this max step size 0.00. I get one more, 0.01. And when I run it now, look at the scope, and I get a much better response here. Okay? And looks like since this only goes from 1.5 to 2 seconds, if I go to parameters, history, see this was checked, so I only see the last 5,000 steps. But anyhow, so that's a common problem when you run a model and you've got a fairly high frequency, even a moderately high frequency input. You just get a garbage output, and the solution is to make the step size, maximum step size, smaller, and you get much better results. And that should wind up this video. I think I'll do one more when I get to it. This is enough to get everybody through homework 1. And I'll do one more example of a model rocket just because it's kind of a fun one, and it just gives you a way. We'll look at it, look at it from a mechanical perspective. We'll have some interpolation blocks and some funny things going on, and just to kind of walk you through it, okay? But that's enough for now. You're probably tired of listening. So